Let's take a look at week 10, example 1. In this problem, we've been given that the sine of theta is 3/5. We've been told that the angle theta lives between pi halves and pi, and we're interested in finding the sine of 2 theta and the cosine of 2 theta. We should notice here that since we're interested in finding information about twice an angle that we already have information about, it seems sensible that we should use our double angle formulas in this case to help us evaluate these quantities. Let's go ahead and take a look at sine of 2 theta first. We derived in our notes the double angle formula associated with sine. Sine of 2 theta will be equal to 2 sine of theta cosine of theta. So it seems that if we're interested in computing the quantity sine of 2 theta, we both need to know sine of theta and cosine of theta. The good news for us is that we already know the value of sine of theta. It's been given to us in the part of the problem. We are responsible for determining the value of cosine of theta. We should always be able to determine one trig function based on our other values here. Let's go ahead and draw the triangle that's associated with the statement sine of theta equals 3/5. Sine of theta equals 3/5. Well, I know that this is going to be our opposite divided by our hypotenuse. So I can tell that 3 will be the opposite side. 5 will be the hypotenuse. What we don't know is our longer leg down here, but a quick application of the Pythagorean theorem should show us that we'll be getting 4 for this unknown leg on the bottom. We have a 3, 4, 5 triangle here. This is good because now I can determine the value of cosine that I need. I've got my triangle here that'll tell me everything I need to know about theta. It looks like we can go ahead and compute our value now. Sine of theta was originally given to us as 3/5. Cosine of theta we can now read from our triangle, but we want to be a little bit careful here. Notice that our angle lives from pi halves to pi. In terms of our unit circle, that means that we live somewhere here. What I know about that region of my unit circle is that all of my sine values are positive because our height is positive, but I can also see that all of our cosine values should be negative since all of our widths go to the left here. So it looks to me like I can use the numbers for my triangle, but I know that I need to go ahead and attach the negative because my cosine values should always be negative within this interval. Using my triangle, cosine of theta, cosine should be adjacent over hypotenuse, so it looks like I pointed wrong there. Our cosine should be adjacent over hypotenuse, so 4/5, which we know to be negative 4/5. Now we just need to multiply up these numbers. Remembering that we multiply fractions straight across. 3 times 4 is 12, 5 times 5 is 25. Finally, 2 times negative 12 will lead us to our final answer of negative 24 divided by 25, negative 24/25. Don't forget that you can always use your triangles here to help you find the other information that you need. Let's go ahead and find our value of cosine of 2 theta now. Our double angle formula for cosine is a little bit different than all the rest. It's the one where we actually have several options of how we can go about computing this. In this case, we were originally given the fact that sine of theta was 3/5. So I'm going to go ahead in this case and I'm going to choose the double angle formula for cosine that involves sine as a function. I'll actually do this one 2 different ways. This is just the first way that I thought to do this problem. Of the 3 double angle formulas for cosine, the one that involves the sine function, the one that has information that I already know about, is 1 minus 2 sine squared of theta. This is good because we already have all the parts that we know. All we need to know is sine of theta, and I know that it's 3/5. The only thing I want to make sure that we're being very careful about here is applying this square. Remember that this square is, in a sense, on the outside. Another way that we could think to rewrite this is like this. This is equivalent. When we put this square on sine, we say first evaluate sine of theta, then square that quantity. First evaluate sine of theta, then square the quantity. All I've got to do now is plug in 3/5 for sine of theta, and we'll have our value of cosine of 2 theta. By squaring 3/5, we get 9/25. 2 copies of 9/25 is 18/25. And when we subtract 18/25 from 1, I'm thinking of 1 here as 25/25. 25 minus 18 is going to leave us with a total of 7/25. Now, this was our route to finding cosine of 2 theta using one of the 3 double angle formulas that's associated with cosine of 2 theta. Just to verify that we could have done this another way, let's go ahead and see a different route to getting this same answer down there. We should be arriving back at 7/25 again. So I'll go ahead and leave that down there. A different double angle formula that we could choose to use here is the double angle formula that says cosine of 2 theta is equal to 2 cosine squared of theta minus 1. The reason why this one makes sense for me to use is because we've already stopped and thought about what this should be here. And remember, we're really maybe thinking to ourselves, this should be a -4 because of the quadrant in which this problem lives. So let's go ahead and apply that here, see if we get our same response. 2 times our cosine of theta angle here is going, our value is going to be -4/5. When I square -4/5, I'll get a 16/25. 2 copies of 16 is 32/25. And again, if I think of 1 as 25/25, then 32 minus 25 is going to leave me exactly with 7/25, just like we saw with the first version of this. There is a third different format of our double angle formula. I don't think it's really going to be the easiest way. Certainly using just the sine or just the cosine is going to be the easier of the two here. But always recognize that you've got some options when it comes to evaluating some of these expressions with the identities that we've seen.